Good morning, everybody. Alrighty. Announcements. Turn my linear algebra 2 brain off and turn on linear algebra 1. Um, Test tomorrow. I actually did. Oh yeah, so first of all, my apologies. Apparently when I was uploading stuff on Tuesday, something broke or the upload failed or it got paused or whatever. And I found out when my class right before this told me because it happened to both of my Tuesday's classes. So they have been re-uploaded. They're probably processing right now. They might actually be finished processing by now. But I do apologize that there was a technical issue um, with the upload from Tuesday's class. But it should be better now. Apparently, someone's going to confirm that, so that's great. But it would have happened within the last half an hour. So test number 3 begins tomorrow as my standard procedure. Once the tests begin, then I shut up about it. So it covers up to including the end of 2.3. As I've mentioned before, and this is true in general, the term tests are as non-cumulative as math can get. In other words, we're not directly testing older material, but you just can't not indirectly test it. It's not like you could never see a row operation again. So that would be test 3. The midterm has been finalized. The announcement went up on Learn, I believe, Tuesday afternoon. That it covers, as I was guessing for the last week or so, up to and including 3.1, but that goes right from the beginning because the midterm will cover the first mid of the term. And finally, just for people's planning purposes, regardless of what happens, that midterm is happening on Wednesday. UMFA job action or no UMFA job action. All right. Obviously the tests as well. So if anyone has any questions about any of that, feel free to fire them off. If not, there's a question on your screen in front of you, or let me double check. Yes, there's a question on your screen in front of you. So give it a shot. We will definitely do 3.2 today. We might start 3.3, but I won't assume any knowledge of 3.3 because it wasn't in the schedule. So we might get to the beginning of 3.3, but the bulk of today will be 3.2. In regards to anything involving the midterm other than the sections that I just mentioned, I don't want to say anything wrong by accident. But what it says in the course outline is what you will need to do. Correct. So to join the midterm, there will be a web, and I'm going to send out. I'm still waiting for one more thing to be confirmed. So between today or tomorrow, I'm going to send out an email, not just to this section, but all the sections with a basically how-to list of how to log on. But the gist of it is you'll log on just like you guys do for your WebEx for the lectures. There will be a list of rooms there. There will be a list of rooms there. And based off of your last name. So it's not based off of the tutorial. It's based off of your last name to join the appropriate room that you're supposed to be in. And I expect a million people going to the wrong rooms, but it is what it is. Will I be in the midterm WebEx? No. There's going to be like 10, 15 rooms. I won't be in all of them. I'll be in one. The odds of it being anybody's particular room is quite small. No, my job is to bounce around and fix issues. So if there's a problem in your room, I might show up. Hopefully I'm not in your room because then that indicates that there were no major problems during the test. I haven't figured out all those details. That kind of is the detail that I'm still trying to work out. That would be my plan, is that everyone joins one main WebEx room and you're divided into breakout rooms. The problem is I would need to be able to, I mean, this isn't your problem, this is my problem, be able to know who's in each room for the invigilators. And that might just be more technical than could be set up. So they might be separate rooms that you have to join the specific room. But if I can make it work, it'll be one room that you automatically get divided into breakout rooms. But that'll be part of the details that I'll be sending out later on today or on Friday. I would love to make that happen. That would make everybody's lives easier. Unfortunately, I can't guarantee that I can do that. Oh, I miss the days where we could just, put up a slide on the sheet and say, go to this room. Maybe next term. All right, anyway, so we got some screens, or some screens. Now I'm really thinking about technology. So we're wanting to find the length of 1, 2, the length of 1, 2, 3, and the length of 1, 2, 3, 4. Righty, so how do we find the length? Or I guess it's kind of implied in the word, but how do we find the length of the vector 1, 2? Not just the answer, but how do we find it? Bingo, it's a Pythagorean theorem. So in terms of the general idea, as we saw last week, we can think of the vector 1, 2 as being the vector that starts from the origin and finishes at 1, 2, and then it just becomes a Pythagorean theorem question. Make yourself this little right triangle. That's a 1, that's a 2, and the length of 1, 2 is the square root of 1 squared, the first component, plus 2 squared, the second component. But geometrically speaking, this is the picture we're looking at. Algebra-wise, it's just the Pythagorean theorem. Any questions about how we find the length of 1, 2? All right, so when I can't draw anymore, what do we do? When we move to R3, where I'm like, I can't draw anymore, you could probably draw it. What changes if we add in a third component? Same formula, add a component. So this is technically the generalized Pythagorean theorem to more than just 2 dimensions, but the idea stays effectively the same. It's going to be the square root of 1 squared plus 2 squared plus 3 squared. And then it just becomes some multiplications and additions. Yeah, so in general, our formula, if we had some vector in Rn, it's u1, u2, all the way up to un, what's that going to equal? Take u1 squared, take u2 squared, and all the way up to un. We just square every single component, add it together. It matches our ideas of length in R2 and R3. It actually matches our length in R1 if you really think about it. But if we go beyond R3, it's more of an algebraic tool than it would be a geometric tool. but the ideas still hold. We just square everything and then add them together. All right, so before we jump on and take a look at the last example, any questions about how we find length? Right. The only thing, and it's unfortunate I didn't think about this when I set up my examples, but the only thing you really have to be careful about is when you square negative numbers that they become positive. Other than people who just don't know what length is, that's probably the most common mistake when doing this is people who square, if one of these happen to be negative, squaring them and then writing it as negative 16 instead of 16, for example. All right, so what do we get for this last one? Anyone have an answer? I guess somebody had an answer. Anyone else have an answer? That's right, with the square root. So 1 plus 4 plus 9 plus 16 is 30, so it's the square root of 30. And remember, these are all positive quantities, the square root. So we haven't seen a lot of square roots in this class, so just a slight theory things, especially for students who did their previous maths internationally. I just want to make sure it's clear. When we write the square root of 30 here, we're talking about the positive square root. We're not talking about both square roots, the plus and the minus. When we write with this notation, we're talking about the positive square root. I do know that notation gets used slightly differently in other places where you might have gotten education. So whenever we're writing square root of 30, we're referring to the positive square root, not plus or minus. It's not plus or minus. All right, so any questions about the concept of length or this little notational quirk? Yeah, so if we wrote x squared equals 10, then we would write x equals plus or minus the square root of 10 if we needed the minus part as well. All right, anyway, back to our regular scheduled linear algebra. So now that we got the answer to all of these lengths, let's use the lengths for something. So compute a unit vector in the same direction as w and a vector of length 5 in the opposite direction. What do we mean by a unit vector? Right. So a unit vector would be a vector whose length is equal to 1. Or magnitude or norm equal to 1. All right, so a couple minutes, give this a try. right. So, how do we find a unit vector that's in the same direction as W? So W is our vector 1, 2, 3, 4. Not sure if you have that in the order that you wanted. Yeah, so we're going to divide the vector by its... Wait a second, divide? Isn't that the evil 6-letter word I said never to use? Yeah. Yeah, we can divide by whatever the norm is, whatever that length is. In this case, that length is 1 over root 30. But this, what I just wrote here, was a lie. What I really meant was W with a hat. So in general, if we want to find a unit vector in the same direction, from a notational point of view, we're going to use this little hat to denote a unit vector. And if we want one in the same direction, we just take that vector and we multiply it by a constant. Specifically a positive constant, because as we saw on Tuesday, you multiply a vector by a positive constant, it doesn't change the direction. So all we're changing is the length, we're not changing the direction. So now we have a vector that has length of 1. Right. Any questions about how we can find unit vectors in any particular direction? Wait a second. We're dividing by a number. Isn't it possible we have an issue there? Gotta be careful when you divide by numbers. No, why can't it be 0? When is the norm equal to 0? Well, yeah, it's undefined. That's the problem. We don't want a concept to be undefined. All right. So this can happen if and only if W is equal to 0. That actually is a property. Yeah, it means it has no length. That's the problem. Or is it really a problem? Yeah, so one of our properties about lengths is the only vector that has 0 length is the 0 vector itself. So why is that not an issue here? Looks like an issue. I'm talking about the formula in general. So for this question, no problem. Sorry, maybe I wasn't clear. For this question, this isn't a problem. I'm talking about the formula in general. Is this a problem for our formula in general? Yeah, 0 over 0 doesn't exist. So, and I really don't want to deal with limits. Technically, this could be handled in a slightly different way from a calculus point of view, but we're not going to do that. This formula. You want to find a unit vector in any particular direction, you take that vector and you divide it by its length. But what about the 0 vector? Yeah, that's my point. What if I said find the unit vector in the direction of the 0 vector? And then I try to use this formula and we got a problem. Yeah, I know, that's the problem. We want to fix the problem. Why doesn't that question have an answer? And it not algebra. Why is that question stupid to begin with? Okay, no questions are stupid. Why does that question not make a lot of sense to begin with? The zero vector has no direction, no specific direction anyway. I mean, whether you think of it as having no direction or all the directions, the point is that the zero vector has no specific direction. So we can't actually even ask the question. Find a unit vector in the direction of the unit vector or the zero vector, because the zero vector has no specific direction. So this formula works perfectly fine except for the zero vector, but the question doesn't even make sense for the zero vector anyway. So for any question where the statement makes any sense, the formula works perfectly fine, and that's the point. Well, the zero vector has a magnitude. It has a magnitude of 0. The issue is that it has no specific direction. But that's not a problem for this type of question, because we couldn't even legitimately ask that question. All right, whatever. Let's do the next one. The question, it's the exception to our vector definition. So we amend our vector definition to include the possibility of the zero vector, which is what we did right at the beginning of this chapter. All right, how do we find a vector of length 5 in the opposite direction as v? How do we find a vector in this? How do we find a vector of length -5 in the opposite? Whoops, you didn't see that. In the opposite direction as v. Thought I was paused. Yeah. So where are we getting -5 from? The 5 kind of makes sense. Where are we getting the negative from? Yeah, negative makes it go into the opposite direction. So -5v. So is that going to give us a vector of length -5? No? Why not? Right. I mean, -5v just takes the length of v and multiplies it by -5. But if the length of v isn't 1, then that doesn't do anything. So what we really need, as people are yelling at me in the chat, which is awesome, is we need -5 times the unit vector in the direction of v. In other words, -5 over the length of v times v, because the unit vector, same formula, the unit vector that we saw before. -5 over root 14 times 1, 2, 3. The point being is that we can make any vector, whether it be in the same direction or the opposite direction, we can scale the thing to be any length that we want. Just by a multiplying by the appropriate number, we can change any vector to any length we want using these ideas, which will come in handy in the next section. All right, if you have any questions about that, let me know. If not, see if you can turn these examples into a property. How can we take any vector and make it any length we want, either in its direction or its opposite direction? Turn this thing into a property. Unit vector of v notation looks weird? Just because one looks like a mirror of the other, or is it an issue with the notation in general, or just how it looks with a v? I will. You don't have to. There's nothing wrong with distributing the -5 over root 14 through to the components. There's nothing wrong with that. But it's also not necessary. People just don't like the hat notation. Never seen people so opposed to the hat. Confused with the unit vector. The hat is just notation. So whenever we have whatever vector we have, whenever we put a hat on top of it, we're talking about the unit vector. We're talking about the unit vector. So in terms of the hat thing, that's just notation that says this thing's a unit vector. That's all the hat is meaning. And a unit vector is a vector whose length is equal to 1. So how do we take a vector v and give it length k in the same direction? Anyone got a formula for me? Everyone likes their formulas. Yeah, it would be k times the unit vector. In other words, k times v divided by its length. And what about opposite direction? Yeah, change the v to its negative. Or change the vector to the negative. So this will be nice when we start talking about projections, which actually isn't the next section. Now I think about it, it's later on in this section. We'll actually get to it today, where we're talking about a projection, which is a vector in the same direction, but the length might change. That's what a projection is. It has more usefulness than just that, but that's what a projection is it's something going in that same direction, but the length might change, which effectively is leading to these ideas, coming from these ideas. All right, any questions about these before we move on? All right, so we talked about lengths. Let's talk about distance. So figure out, here's a couple questions right here. See if we can find the distance between these points or between these vectors. Which one of those three is the distance? Just the distance formula. Well, where does that distance formula come from? Alrighty, so I'm not going to assume knowledge of a distance formula. If you don't know what a distance formula is, you're about to. So we have the vector, the point P and the point Q. So P, 1, 2, 3. Q, which is 3, negative 2, 1. Or is it negative 1, negative 1? So geometrically speaking, vector-wise, I know there's a formula for a distance formula. This is actually where that formula kind of comes from, but there's just the connection there. Someone's saying we want to find the vector. Which one? Do we want to find PQ or do we want to find QP? Very good. Doesn't matter. Doesn't actually matter. PQ and QP aren't the same vector, but we're concerned with the length of it. We're not concerned with the vector itself. So our distance is the length of PQ. So if we want to find the distance between any 2 points, we can find the vector connecting those points and find its length. In other words, that's the length of, as somebody mentioned, 2, negative 4, negative 4. We have our 2 points here, P and Q. We can find our vector connecting P and Q, but as somebody mentioned, it doesn't really matter. We could have used QP if you wanted to. and then we just find the length of whatever that vector is. So we get it by subtracting the components, the vector itself, and then we find its length. So if you used QP instead of PQ, you would have actually got the negative of this vector, but it wouldn't have affected the length. And then it's, what, 2 squared, negative 4 squared, and negative 4 squared. So this is how we can find the distance between any 2 points, or any 2 vectors for that matter. We don't really distinguish between points and vectors very much. All right. So any questions about these ideas? Famous last words. All right. So just a little squaring again. Be careful. Common mistake would be to say negative 4 squared is negative 16. So just be careful with that. Great question. How did I get 2, negative 4, negative 4? Yeah, so this is the ideas we saw back on Tuesday. If we're given 2 points, we can find the vector between these points by subtracting those components. So 3 minus 1 is 2, negative 2 minus 2 is negative 4, negative 1 minus 3 is negative 4. What's coming up? Well, the second example. Anyone have an answer for the second one? Ideas are the same as what we kind of just did here. Does it have to be a lowercase d? I'm just sticking with the notation in the textbook that talks about the distance between 2 vectors. So d of uv is the notation we use for the distance between 2 vectors. I did say famous last words, yeah. Yeah, so again, whether we're doing points, whether we're doing vectors, doesn't really make a difference. We still find the vectors connecting. If you want a geometric idea as to where this is coming from, we're just connecting the ends of the 2 vectors. If they both started at the same place, probably the origin. We're connecting. So if we're thinking about it, here's the origin, there's v, there's u, and we're talking about this distance. So if you're wondering what we mean by the distance between 2 vectors, we're talking about the distance between their the ends of those vectors, the terminal points of those vectors if they started at the same place. Obviously, this is 4 dimensions, so you kind of lose that, but algebraically speaking, that's what we're doing. As an algebraic thing, you subtract the vectors, you find its length, same idea. All right, so any questions about lengths and distances? We're going to see a lot of distance stuff for the rest of this section here. All right, so that brings us to, so we've talked about how to add, we've talked about how to subtract, we've talked about how to multiply vectors by scalars, what it meant geometrically, what it meant algebraically. What haven't we done yet? Even if we're relating it to matrices and the type of operations we did with matrices. Yeah, how to multiply two vectors together. How to multiply two vectors together. Which leads us to our dot product. That's right. So just like with adding, subtracting, and multiplying by a scalar, we thought of those things algebraically, we thought about those things geometrically. So it might not be a surprise that we're going to do something similar. So in this section, we actually have two ways of looking at the dot product. So this first way, what's the benefit? What's the benefit of looking at that first way of viewing the dot product? Get used to it. Yeah, we're looking at the magnitude. What else are we looking at? Yeah, we're getting stuff from its direction. Angle 1, direction 2, angle between them. That was awful. All right, but the point being is that we're getting this more from the geometric way we view vectors, their lengths and their directions. We're kind of getting the first equation from that direction, which is very nice for geometric reasons. What's the nice thing about the second way of doing it? We need an angle for the second way? Oh, doesn't need an angle. There we go. Yeah, the idea is the second one is so much easier to compute algebraically. And that seems to match our pattern. We have the geometric nice things that we're going to use, and the nice algebraic way is how we work with it. And the point being is, and I go over this proof in the video, so we won't rehash it here, is that these things are exactly the same. So the video talks about exactly why they're the same. All right, so I'll come back to that. So give this question a try. See if you can actually solve this using both techniques, the geometric idea and the algebraic idea. Because if you ever needed convincing why we really like the algebraic way, you might come up with that reasoning after this one. So see if you can find the dot product using both techniques for this particular question. All right, so should we start with the easy way or the hard way? And even the hard way is not too hard in this example, but the super easy way and the slightly more annoying way. Start with the hard way. Sounds good. You can probably guess which one the hard way is going to be. That's our length of u times the length of v times the cosine of the angle in between. Fortunately, we can get these things geometrically. Here we go. Here's u. Yes, it is. But that was for effect. So here's u. And 1, 1. Here's v. And here's the angle between them. What is that angle? Sure, but for these particular, you can do better than that. No, not 3 pi over 2. 3 pi over 2 would start here and go all the way to there. In degrees, we seem to have gotten 135 degrees. There's no calculus in this class, so if you want to use degrees, even though it breaks my heart, I won't stop it. If you live in a radian world, as I do, it's 3 pi over 4. How did we get that? Fair enough. Fair enough. Where do we get 135 from here? Or maybe here's a better, well, I guess I could leave that there. I'm hoping everyone can agree that this angle right here is 90 degrees. If not, we have bigger problems in this class. All right. So that's 90 degrees. So the real question is, what is this angle? And here's why I specially chose 1, 1. So this is a little less obvious. So if this is the vector 1, 1, what is this angle? Now, some people are saying 45 degrees, so why is it 45 degrees? Or pi over 4, however you want to phrase it, degrees or radians. How are we getting that angle? Why is it halfway? Right, because the x and the y are the same. So we don't actually need to go to trig to see that. Because if the x and the y are the same, what type of triangle do we have? I mean, it's a right triangle, but what other type of triangle do we have? Isosceles triangle. Yeah. 1, 1. It's isosceles. These sides are the same, which means that angle and that angle are the same. And we can use that to realize this is 45 degrees. Or, little trigonometry, tan theta is 1 over 1, and you can solve for theta is equal to 45 degrees that way as well. So that's why this angle here is 45 degrees. Add that to the 90, just because it's pointed straight down. And that's why the angle is 135 degrees. Or 3 pi over 4 if you live in a radian world. Sometimes I miss calculus where I can just say to students, learn radians and be done with it. But the idea is we get the angle in between, which we need to if we're using this geometric way of calculating it. So any questions about how we found the angle? All right. So The length of u, we can probably get that right from the picture, although we could use the formula as well. What's the length of u? Yeah, again, we could think of it, think of it geometrically. We're going from 0, 0 to 0, negative 2. Alternatively, we could just blindly use formulas. Don't forget the square root. We get that it's equal to 2. V, again, same deal. We could use some of the algebra. Otherwise, some of the geometry to reason out that it's root 2, or just straight up use the formula. So in other words, u dotted with v is equal to 2 times the square root of 2 times cosine of 135 degrees. What is cosine of 135 degrees? And by the way, this is expected knowledge. Not 1 over root 2, no. Close, though. Yeah. That's 2 root 2. No, it's not. We get our answer of negative 2. So if you're wondering where 1 over root 2 came from, it's your whole unit circle thing. 135 degrees. Cosine is the x, that's why it's negative, etc., etc. In this class, rationalizing is not a necessary thing. It's also not wrong. In this case, it just made them cancel anyway. It's not wrong to rationalize. It's not necessary to rationalize either. There are other contexts where it's more important. In this class, it's really not going to be. All right. So I'm glad we did this once and we'll never do it again. Because the algebra way is so much nicer. 0, negative 2 dotted with 1, 1 is 0 times 1 plus negative 2 times 1, which is negative 2. But we do actually get that they're the same both ways. And the full proof is in the pre-lecture video. But the idea is that we always get the same thing. And so the connection is important, but it's important for a slightly different way. Alrighty, any questions about how we can find the dot product? No, you do not need to use I gotta phrase this right. You aren't expected to use the geometric way to compute the dot product. You will be expected to use the geometric way to use the dot product for the types of questions we'll be talking about in just a minute. All right, but any questions, especially the algebraic way, because that's what we're going to focus on. Again, geometry for applications, algebra for nice calculations. That's our general ideas we're getting out of all this vector stuff. All right, so before we move on to the next question, I did want to kind of address two things. Common things, annoying things that make students lose marks. Number one, this is a math class, so notation is very important because we have two ways of multiplying things now. We're going to have a third by the end of this chapter. But right now we have two ways of multiplying. The dot product we just talked about and scalar multiplication that we talked about last class. We need to make sure our notation treats those things differently. Like I said, a third way that we'll see by the end of this chapter. This right here is garbage. Garbage. Why is that garbage? Right. There's no such thing as a dot product of a number with a vector. No such thing as the dot product with a number and a vector. When we use scalar multiplication, it's the number beside the vector. 2u, not 2.u, 2u, 3u, negative 5u, not negative 5.u. Right. So for those of you who, because we do it with numbers, so I'm not saying I'm saying it's understandable that you might flip between these things because we're so used to doing that with numbers. But for vectors, because we're going to have 3 different ways of multiplying, it's very important that we're writing them in 3 different ways. So k dot u is wrong. The dot is for the dot product. We want scalar multiplication. We need to write it as the number beside the vector. In the same way, uv is also garbage. We have 2 vectors and you write them next to each other. What on earth does that mean? It doesn't mean anything. If you're writing them next to each other, yeah, that'll show up later in this chapter as well. So we have, if you have u and v next to each other, that's just wrong. We need to use, if we're doing the dot product, u dot v. Or something else later. But the point is that notation with these things is very important. Unlike matrices, with matrices, there was only one way to multiply matrices. For vectors, there's going to be different ways of multiplying matrices together, or vectors together, which means that we need to be very careful with how we write it. You write it wrong, then we're not, accurately saying the actual calculations that we're doing. So scalar multiplication, no dot, dot product, dot. And some other product later in the chapter will have its own notation as well. All right, so any questions about the notation? All right, and secondly, before we move on to our next example, we've seen the dot product in this class before. I didn't call it the dot product, but we've seen the dot product in this class before. Right. The idea of, at least the algebraic way, we haven't seen the geometric way before, but the algebraic way, we take individual entries, multiply them together, move to the next one, multiply them together, move to the next one, multiply, together, and then add them. We called that multiplying a row by a column when we multiplied matrices. And so any time before where I said row I times column j, what I really meant was the vector that represents row I and the dot product with the column vector of j. Except we didn't say vectors, we called them rows and columns. So now, and I've just been struggling not saying the word vector, and I probably failed a couple times. But yeah, when we were multiplying matrices, what we really were doing was taking the row vector dotted with the column vector. We just didn't call it that because we hadn't done vectors yet. So yeah, they're absolutely related. So any dot product is really just a row vector or a row multiplied by a column. Good. All right, so any questions about these ideas before we move to the next example? All right, so as it kind of mentions here in context, yes, we could use the angle to find the dot product, but what we're really going to do is use the dot product to find the angle. So all the stuff that connects the dot product with the angle, while it's really, really ugly, as we saw in our last example, to use the angle to find the dot product, we're really going to use that equation in the opposite way. So see if you can figure out how to use that equation to find the angle between these two vectors. I didn't say failed necessarily. I might have failed. Yeah. So the idea behind this, so like I said before, we're really not going to use that geometric definition of the dot product to solve for the dot product. We're really going to use that geometric definition to use the dot product to find the angle. So somebody wrote the formula there, and that's great. So if we rearrange this thing, and again, we're solving for the angle. So what do we do with the stuff in front of that angle, or at least the cosine of that angle? We divide. Oh, are we dividing by 0? What if we're dividing by 0? In this example, we certainly aren't. In general, if we're thinking of this as a general formula, could we ever be dividing by 0? Same rant as earlier. All right. So again, as before, the only way we could be dividing by 0 would be if one of these vectors was the 0 vector, maybe even both of these vectors was the 0 vector. But is that even a reasonable question to find the angle between some vector and the 0 vector? So would it be a reasonable question to ask this? No, why not? Why is that not a reasonable question? Yeah, the angle comes from the direction. The 0 vector has no specific direction. So beyond the formula just failing, the question just has no reasonable answer. All right, so that's good. You don't want to create a formula that doesn't always work. Right? You create a formula that, is like, all right, this will solve the question some of the time. That's a problem, right? We want to make sure that what we're doing here solves the question all of the time. And we are getting that as well. All right, so let's compute stuff. What's u dotted with v? For now, back to this specific example. What's u dotted with v? One times 2, 1 times 1, 2 times negative 1 is 2 plus 1 minus 2. That's equal to 1. What's the length of u? Square root of 6. That's 1 squared plus 1 squared plus 2 squared is root 6. The same length calculation that we've seen quite a few examples of. And what about the length of v? Yeah, same thing. Careful again. It's negative 1 squared. So it's 4 plus 1 plus 1. The common mistake here would be to get root 4. instead of root 6 because of that negative. We're squaring everything, so everything's positive. So in other words, the cosine of theta is 1 divided by the square root of 6 times the square root of 6. What's root 6 times root 6? 6. Again, you can think of it in two ways. It's root 36, and the root 36 is equal to 6. That's one way you can think about it. I like it a slightly different way. That's another way of thinking about it. No? Okay. Well, we get 6 anyway. Yeah, we can think of it as the square root of 6 squared, and the squared cancels the square root. But yeah, we're not done yet, but just the square root stuff. All right. Is there a nice value of theta? My definition of nice, not your definition of nice, where cosine of theta is equal to 1 over 6? Can we say it's like 45 degrees or 60 degrees or something? Something real nice? Yeah, it's not on my special values list. So actually, compute the angle between, yeah. So that would just be cosine inverse of 1 over 6, and it's perfectly fine to leave it like that unless it's one of our special values. Because if I see an answer of, I don't know, 78.54321774, I'm not saying that's what the answer is. You know exactly what I'm going to think. That somebody's been using unauthorized material during their test. So if you want to put a big flashing red sign on you that says that you're using a calculator when you're not allowed to, go ahead and toss that into a calculator. No, in this class, and this is a general thing, in this class, 2 words, exact answers. Exact answers. This is exactly what the answer is. Cos inverse of 1 over 6. You put 3 decimal places and stop, that's an approximation. So we keep our answers as exact answers. I'll address the cos values that you're expected to know in just a second. Other than that, any questions about how we solve this? Your calculator is not going to give you an exact answer. All right, so the ones that we expect you to know, again, in degree land, are things like the zeros, the 30 degrees, the 45 degrees, the 60 degrees, the 90 degrees, and so on. These are the ones we're expecting you to know: sine, cosine, and tangent, which is sine over cosine. That's what we expect you to know, both ways, backwards and forwards. So those are the ones that you're expected to know. So sine of 30, or sine of 0 is 0 over root 2. Sine of 30 is 1 over root 2. Sine of 45 is, or sorry, not 1 over root 2. That's a lie. Over root 4. 1 over root 4. 2 over root 4. Or root 2 over root 4. Sorry, my mnemonic device is failing. One question here. All right. Root 0 over 2, root 1 over 2, root 2 over 2, root 3 over 2, root 4 over 2. There we go. Cosine is root 4 over 2, root 3 over 2, root 2 over 2, root 1 over 2, and root 0 over 2. There we go. So basically, these are the ones that we're expecting you to know, and also with if they're in different quadrants, some of them are negative, like we saw with 135. What is cosine? Root 0 over 2. So yeah, 0. Anyone see a pattern? Probably not. All right. I was going for more than that, but sure. All right. You have to be able to do, let's say, those were the ones in quadrant 1. So those were the ones over here in quadrant 1. But you'd have to, the appropriately other angles in the other quadrants as well. All right, anyway, so the last question that I have from this section. So using the ideas here, oops. So we know that u dotted with v is equal to the length of u, the length of v, cosine of theta. Looking at this, or looking at the one where we divided them, either way, how big can u, and small for that matter, how big and small can this dot product be? That's how big the angle could be, but not the dot product. Yeah, the largest angle. Remember, theta is the angle between two vectors. So if they're pointing in opposite directions, they're 180 degrees apart. Otherwise, the smallest angle is somewhere in between 0 and 180 degrees. 0 if they're going the same direction. What's between -1 and 1? Something's between -1 and 1. What's between -1 and 1? We know cosine of theta is between -1 and 1. The angle itself is between 0 and 180 degrees, or in radian world, 0 and pi. Cosine of theta is between -1 and 1. That's just rules about cosines that you would have seen in high school. Cosine is between -1 and 1. So what does that tell us about u dotted with v? How big could it get? If the cosine is at most 1, then what's u dot v? I guess in theory that's true. We want to do a little better than that. We do not need squeeze theorem. If you don't know what squeeze theorem is, go take calculus. We're not doing it here. First of all, I don't know why people are saying greater than 0. No rule is saying that it has to be greater than 0. Yes, it's going to be a real number. Yep. So if cosine has to be less than 1, the only thing there is it can be equal. It doesn't have to be strictly less than, but if u dot v is equal to the lengths multiplied times something that's less than 1, then it has to be less than or equal to the product of those lengths. Similarly on the other side. So the dot product can absolutely be negative. The dot product can absolutely be negative. There's a couple people said it had to be greater than 0. That's not true. In fact, we saw earlier, we got a dot product of -2. Right? There's nothing saying the dot product can't be negative. What this is saying is that the dot product can't be any more than the two lengths multiplied together. And in fact, it does equal it sometimes. When is these two actually going to be equal? When would those be equal? When cos theta is equal to 1, absolutely. When is cosine of theta equal to 1? When theta is 0, okay. So when u and v are going in the same direction. They don't have to be equal, but going in the same direction. So u dotted with v is equal to this product if the angle between them is 0. In other words, if u and v are going in the same direction. Conversely, when is u dotted v equal to the negative of that product? When they're going in the opposite direction, that's right. When they're going in the opposite direction. This rule here, this is actually called Cauchy-Schwarz, which is more powerful than it seems, the Cauchy-Schwarz inequality, and I think I'm spelling the name wrong, which means I think I get fired for spelling a mathematician's name wrong. No, I got it right. Beautiful. Cauchy-Schwarz. Two mathematicians named, hyphenated together. Cauchy-Schwarz inequality. Which in this class doesn't look like it's particularly powerful. And unfortunately, we just really won't see the power of this particular inequality in this class. But it is something. While it seems so many years ago now, I used it in my thesis. Back in 2000 something. But the idea is this particular inequality is a very powerful one and quite useful. All right, so any questions about this? All right, so a few more things to piece together in order to give us a launching pad for Tuesday's class. So we talked about if the angles go in the same direction. If the angles go in the same direction, what does that tell us about cosine of theta? If they're going in the same direction, theta is 0. That tells us cosine is 1. And similar in the opposite direction. So let's see if we can fill in these three blanks. No. Let's see if we can fill in these three blanks as a launching pad for what we're going to talk about in section 3.3. Acute, if you're not sure what that word is, acute means between greater than or equal to 0 or between 0 and 90 degrees. So if the angle between them is between 0 and 90 degrees, what does that tell us about the dot product? I guess I should have said about the dot product. If the angle is between 0 and 90 degrees, what does that tell us about the dot product? No. See if I can write down our geometric formula. No, I can't. U, V, cosine theta. Right here. If the angle is between 0 and 90 degrees, aka it's an acute angle, what does that tell us about this dot product? If the angle is between 0 and 90 degrees, trig fund. It's positive, yeah. Cosine of any angle between 0 and 90 degrees is positive, and multiplying by lengths is going to keep it positive. So if the angle is between 0 and 90 degrees, this dot product is going to be positive. When do we get a right angle between 0 and V? We get a right angle between 0 and V. What does that tell us? Yeah, that happens when the dot product is 0, because that would mean cosine of 90 degrees is equal to 0. Again, more trig fun. And lastly, obtuse. Obtuse means between 90 and 180 degrees. And what would that mean for our dot product? That would mean that it's negative. That's right. So even if it requires more calculations from the dot product itself, whether it's positive, it's negative, or it's 0, tells us approximately what type of angle we're talking about, especially this second one, which is so special, we're going to give it a special name. We say U and V are orthogonal if the dot product between U and V is equal to 0. And we'll talk a lot more about that on Tuesday. If you have any questions, please let me know. If not, that's it for today.